This past summer, at Bosch Solar Energy in Germany, the business development team developed a market strategy for the US market to increase the amount of solar photovoltaic energy online in the United States. The first phase of our research looked at developing a US market model for the residential, commercial, and utility segments to project the amount of solar power online from 2012 to 2020. We looked at different drivers and barriers of the market, including federal and state level incentives, the price per watt to bring a solar system online, and the investment from private sector to create different scenarios and project the amount of solar power online during the next few years. The second phase of our research included creating a 50-state ranking system. This ranking system was based off of quantitative research, which we used different data to rank all 50 states based on different variables. For the retail market, we focused on 7 different variables that were correlated with demand, and for the wholesale market, which was utility-sided systems, we focused on 3 different variables. In the end, we were able to create a model that, and finally, we looked at US public opinion and the 2012 election and the different implications. We looked at different public opinion polls to look at US public support for different incentives for solar energy, and also at the outcomes of the 2012 election, and looked at what policies could change at the federal level depending on who won. Finally, we did an analysis of third-party system integration in solar leases and power purchase agreements, and also looked downstream at project development and what profit margins could be achieved if the solar manufacturer integrated downstream from solar module sales to offering full project solutions.
Solar power provides probably the best option for achieving cost-competitive renewable energy with fossil fuels. But increasingly, even though there's been significant progress, all the low-hanging fruit has been found, and it's hard to find that next innovation which is going to really lower prices down to be competitive with fossil fuels. And here's a big innovation. Current solar panels only use up to half of the sun's energy. All the infrared light is not harvested at all. So there's a way you can do that. You can use upconversion. And what upconversion is basically a fluorescent layer which you put behind a solar cell and instantly provides you an efficiency boost by absorbing that infrared light and re-emitting a visible light back up into your solar panel. However, solar panels are very complex engineered devices, and no one's really sure how they interact well with upconverters. So what we did, just like engineers have CAD software lets you see in real time in 3D what's going to happen before you actually make a product, we made a CAD system for simulating upconversion with solar cells. So you can see for any kind of solar cell you want, how would it do with upconversion, what the benefits would be, and what the challenges are. And we did this for all the major technologies, for silicon, for CAD-TEL, for SIGs, for dye cells. And we show that really the best potential option is using dye cells. Upconversion with dye cells will get you from 12%, the current world record, up to about 15%, which is a huge benefit. And this will hopefully bridge the gap between research innovation and market success.
Hello, my name is David Gaker, and I want to talk to you about how household appliances can be designed to work together not just aesthetically, but also functionally. Household appliances are often designed and sold together on the basis that they complement one another via their materials, the color schemes, their sizes, etc. But even though these machines serve different purposes, such as washing clothes or heating food, they often utilize similar underlying processes, such as controlling water flow, transferring heat to or from some medium, etc. This system of independent operations is suboptimal both in terms of energy demand and in the service that it provides to us, the users. For example, refrigerators often just dump their waste heat directly into the air of the kitchen, which is already too warm anyway. And water heaters, completely independently, use the electricity to, as their name implies, heat water. What I'm proposing is that if we could use the cold water input to the water heater as a heat sink for the refrigerator, it would drastically increase the efficiency of each appliance, saving the average household $400 per year. Not to mention the additional benefits of reduced fan noise in the kitchen and reduce demand for air conditioning. Needless to say, the gains in industrial and laboratory settings would be substantially larger. Such is the potential when appliances are designed to work together.
So my name is Gao Liu, and I'm going to talk about our invention of the conductive polymers for lithium-ion battery application. So these inventions really came out of our work in the DOE-funded Battery for Advanced Transportation Technologies program at Burke Lab, and also was partially supported by the UC Discovery Grant. So first, I want to thank this agency for financial support. The conductive polymer binder technology can significantly enhance energy density of the rechargeable lithium-ion battery. In particular, this invention is in regard to the anode side of the battery. We have developed electrically conductive polymer binder materials. The band gap of this polymer is synthetically controlled to be compatible with the anode working potential of the lithium-ion battery. These polymers were designed to be used as both binder and conductive additive for high-capacity anode materials, such as silicon and tin. The anode made of this conductive polymer and silicon materials delivers 10 times specific capacity that of the current graphite anode. The battery built with this technology, in coupled with an advanced cathode, could double the energy density of the current lithium-ion battery. So what does this mean in a practical application? The new battery will enable an electric vehicle to drive twice as far as the current battery can do in one charge. And it all starts from these special conductive polymer binders. Thank you.
The energy crisis is striking the world. Prices are soaring, and every day more and more greenhouse gases are being emitted into the atmosphere. We cannot let this happen any longer. We need to react. Here at UC Berkeley, we're building the future of nuclear power. We're developing an innovative reactor design called the Pebble Bed Fluoride Salt-Cooled High Temperature Reactor, or the PBFHR. The PBFHR is inherently safe due to its passive heat removal system and its high fuel melt temperature margin. It is more efficient than ever thanks to the fluoride salt coolant, which has a better capability of transferring heat than water. We are also using twisted tubes in our heat exchangers to further enhance heat transfer and efficiency. The high output temperature from the PBFHR allows for process heat production, opening up a plethora of markets. The PBFHR is also economical thanks to its modularity, its compact size, and its superior efficiency. Today, supported by the Department of Energy, we are working with national laboratories, other universities, and world experts to turn this reactor into a reality. I myself am working on computer codes and experiments that simulate passive safety features such as natural circulation, which require no AC power input, thus increasing the overall reliability of our reactor. The future is today. Come visit us at the Burke Innovation Expo on Thursday, October the 18th. We very much look forward to your questions.
Ladies and gentlemen, for your enjoyment, I've prepared a presentation on microgrid deployment. My name's Sustainable John, and I ain't that smart a kid, but I do know a thing or two about the smart grid. Let me lay it out in 3 basic functions and explain why we're at a critical junction. First, the traditional grid needs better operation, more accurate and smooth with operator visualization. Demand and supply need to talk to each other. Just think of all the energy information to discover. Third, we need more decentralized generation, the most important step towards a new energy nation. This is where microgrids play a crucial role for cleaner power, increased reliability, and control. A microgrid is a group of resources and loads. It can operate grid-connected or in island mode. Think about CHP, fuel cells, and solar PV working together with flexible loads and maybe a battery. We've developed great control and storage technologies, but what I find we need is better governance and policies. My team performed an international assessment of experience to date on things like grid interconnection. We looked at the benefits that microgrids produce and the suite of incentives we would need to introduce to ensure that no barrier, utility, or regulatory would stand in the way of microgrid deployment. So come on down to the Burke Innovation Expo. Please check out my poster, my rhythm, my flow. I know you won't be disappointed. I don't kid. We're gonna imagine the future of the microgrid.
Hey guys, I'm Kyle Tom. I'll be talking at the Burke Innovation Expo next Thursday, talking about cadmium oxide use and TCOs. So, the first question you're gonna ask me is, what's a TCO? Well, TCO stands for transparent conducting oxide. It collects current from solar cells. It goes right underneath the glass part that's used for protection. The next obvious question is, why are TCOs even important? Don't we already have methods? Well, the current method we use now is to have a metal grid that runs across the cell. Unfortunately, since metal is opaque, it actually causes some of the sunlight to be blocked from reaching the solar cell, and it decreases power output, and that's bad. TCOs will try and fix this by being both conductive and transparent. Now, why is cadmium oxide so great? I mean, we have lots of materials. What signifies this one as being important? Well, the current one we use now is ITO, indium tin oxide. The reason this isn't so great is that indium is very expensive, there's not a lot of it, and a lot of different electronic applications use it, so it's very competitive to get. Cadmium oxide, on the other hand, is cheap, there's a lot of it, and it actually rivals the properties you get from ITO. So some of the current research we're having right now is to optimize the transparency and the conduction, since the more conductive a material is, generally, the less transparent it is. So some things we're doing now is doping it with different materials such as magnesium, copper, silver, and zinc, as well as annealing it, heating up, seeing how that changes properties, and also radiating it, just blasting it with neon radiation. The last thing we're doing is also exploring low temperature, low cost growth techniques such as sputtering. So I'll see you there.
Hi, my name is Paul Wolski, and I'm a grad student in comparative biochemistry. I work at the Energy Bioscience Institute, which is a facility that was funded by over a $500 million grant to do biofuels research, and some of that money is also at Berkeley and Illinois and at the Lawrence Berkeley National Laboratory. My research focuses on converting plant waste into usable biofuels. Specifically, it's to convert cellulosic material into sugars, which could then be fermented into biofuels. My research has been focused on trying to combine the pretreatment of the cellulosic material, which is the converting the cellulose or plant waste into a easily digestible form. So to back up a little bit, the cellulose is actually a major component of plant material. It composes over 40% of the dry cell mass of plant material, and it's actually wasted every year. So in corn ethanol, what happens is that the corn kernel, which is actually edible, is used for biofuels, but the rest of it, which is mostly cellulose, is wasted. Our research is trying to convert a plant material which is renewable and reusable and gives a more output per unit area of cellulosic material. So what we're trying to do with that is I am trying to combine the pretreatment with the enzymatic digestion using what's called ionic liquids, which actually dissolve the whole plant material. Great motivation for that is it eliminates any contamination, and it allows for a combination of the pretreatment and enzyme hydrolysis to give a much more effective and economically effective biofuel. Thank you.
consumers always want their electronic system to be have more functions, but at the same time also need to be lower power, longer battery life, and also need to be lighter and thinner. Now, to meet all of these demands, we need to design the electronic system in here to be not only energy efficient, but also need to be area efficient in order to leave more space for the battery to have a longer battery life. Now, while all other electronic components in here are catching up, trying to make it very well and to fit in smaller area and going with the scaling of technology, the power management is actually very slow in this renovation of integration, everything together. For example, all the power management units now are implemented in a separate chips with a lot of off-chip components, taking a lot of area. So the area spent on power management is either fixed or not scaled as fast as the other functional chips, making its relative area to increase from about 10% in the iPhone 3GS to 20% in iPhone 4S. Now, our solution is we will integrate all the power management unit onto the functional chips so that we remove all the off-chip components, making it totally kind of no mass, no area consumption here. And at the same time, since we benefit from the co-integration, we can make it much more efficient because we kind of point of load delivery the power right to the load so that it's energy efficient and area efficient. We expect to save up about 40% of the total power of the system with this solution. Thank you.
My name is Kyu Taek from Lawrence Berkeley National Lab. The title of my poster is Performance Improvement of Hydrogen Bromine Flow Battery. Let me explain about the presentation. Renewable energy resources such as wind and solar are gaining attention these days a lot due to the environmental concerns. But the electricity generated from those renewable resources are not constant and even fluctuated depending on weather conditions. So we need system to store electricity when it's generated and supply it more reliably when it needed. At Berkeley National Lab, we are developing new system called flow battery, which has two components. One is the cell hardware for generating electricity, and the other is the electrolyte storage device for storing energy. In order to reduce system cost for actual application, the size of expensive cell hardware need to be decreased, which can be achieved by improving cell performance. We have been developing flow battery system with hydrogen and bromine, and we achieved the highest performance in the world. In this poster presentation, I will explain the detailed approach and method to achieve that high performance. Thanks.
Today, almost 1 billion people lack proper access to water, and 1.5 billion are not connected to electricity. In many cases, these are the same people, and they often live in rural areas of developing countries. This is because water and energy are strongly related. You need water to generate electricity, and you need energy to supply water. That's the water-energy nexus. This is of course a challenge, but it can also be seen as an opportunity. In developing countries, people actually pay a lot for the first few kilowatt hours of electricity, from very inefficient sources actually. This provides them with the comfort of appliances like lights, cell phone, and TVs, and often allows them to start a small business. In fact, electricity is often perceived as an instrument of social mobility. At the same time, although water is a vital necessity, people are reluctant to pay for it. They would rather walk for miles to collect unsafe but free water than pay for water supply. This is a real paradox, and there lies the opportunity. So my research considers a simple technology that addresses this paradox in alpine valleys, killing two birds with a single stone. There, water sources are usually high above the villages, and turbines are included in the water supply system to transform the excess pressure into electricity. Such systems spurred local economic development and allows water to be provided at a very low cost. Strangely, this concept is very rarely implemented in developing countries. Nailing down the single reason for that is very difficult, but I am mostly interested in finding out where the concept will be feasible. Mountains in developing countries are very difficult terrain to do research in, as very little field data are available. Fortunately, these regions are now covered by good satellite data. My plan is to use them to model stuff like river discharge, household demands, or infrastructure costs at a large scale. This will allow to map out for practitioners not only where the turbines are feasible, but where the economic situation is the most beneficial. Today, millions of people lack access to basic necessities because of a narrow single-purpose approach to urban rural infrastructure.
Everyone poops. In the US, this waste goes through pipelines into wastewater treatment plants. But in developing countries, this may not always be the case. Waste may be dumped into oceans, surface waters, or into large storage ponds. This waste just doesn't go away with the flush of a toilet. Instead, it persists in the environment and poses huge health and environmental risks. Now, what if I told you that we could turn human waste into usable energy?
We've spent past 3 months researching this topic in Ghana. Our research has shown that we can certainly turn human waste into renewable energy source that is competitive with non-renewable energy options. Our fecal fuel has a calorific value ranging between 18 megajoules per kilogram and 20 megajoules per kilogram, which is as competitive as wood pellets and grade B coal. It also has the added benefit of pathogen inactivation as part of the drying process we undergo. This will be a very desirable energy option for cement kilns and boilers in Africa, where solid fuel is a very increasingly costly and scarce option. Also, this may help European industries meet its European Union's renewable energy goal of using 20% renewable energy by 2020. Considering that fecal fuel is a very inexpensive feedstock, we think that our fecal fuel will be very cost competitive at the same time.
Everyone poops. That means that we will have an unlimited feedstock with which to create our energy. And by producing and distributing this energy, we will help promote demand-driven sanitation and use of alternative and renewable energy in a rapidly developing world.
Thank you very much.
Hi, my name is Zach Baer, and I'm a graduate student at the Energy Biosciences Institute, right here on campus at UC Berkeley. I'd like to talk to you today about my project, Integration of Chemical Catalysis with Extractive Fermentation to Produce Fungible Fuels. The real problem that this project focuses on is the fact that we don't have a sustainable, economical approach in order to mitigate or significantly reduce the amount of fuels we use from petroleum. And I'm not just talking about gasoline, I'm talking about jet, I'm talking about diesel. Though our approach is an integrated one, in that we're going to use biology, and we do use biology, to take sustainable, renewable sugars derived from plants, ferment them into small hydrocarbons, and this process has been done for over 100 years on large scale, well known, and using that process, these small hydrocarbons can be thought of as gasoline molecules, and they have been used for that. But we see them more as building blocks. And if you look at them as building blocks and start to think about the chemistry you can do with them, you realize that you can start adding on to one another and make larger and larger compounds. These start to look a lot like jet and diesel. And so now we have a chemical catalysis approach and a biology approach. The two environments which these operate in, quite different. So we need a technology that integrates them. And that's where we turn to liquid-liquid extraction, which can best be described by what I have here, which is cells growing in an aqueous phase, and then a liquid extractant, an oil sitting on top, which is non-toxic. The cells don't feel the oil, but it pulls the hydrocarbons up, away from the cells, away from the water, and into a phase in which the catalysis can work. We've already achieved yields that are near theoretical, and we're talking about a sustainable process So we're almost there. It just takes a little more optimizing. I look forward to seeing you at the Innovation Expo, and feel free to ask questions. If you have a great day and enjoy the symposium.